What if the thing that kept people alive and clean for centuries wasn't a product you could buy, wasn't a formula a chemist invented, wasn't something you needed a factory to produce? What if it came from the bottom of a fireplace and the scraps left over after butchering a pig? You've probably heard that people used to make soap from ash and fat, and your mental picture is probably something like, you mix the two together, let it sit, and soap appears. That picture is wrong. Not dramatically wrong. Just wrong enough that you couldn't do it yourself, and wrong enough that you'd miss the most interesting part of what's actually happening. The simplified version persists because it is mostly correct in its conclusion. People did make soap from ash and fat. It did work. It cleaned clothes, cleaned skin, and kept infection at bay across centuries of daily life on farms, in frontier cabins, in medieval villages. The simplified version also has a kind of beautiful simplicity to it. Two things everyone had, combined into one useful thing. That's a satisfying story, and it's not false. The reason it gets taught this way is that the full version requires chemistry, and most of the people who needed to know how to make soap didn't think of themselves as chemists. They thought of themselves as keeping their family alive. So the knowledge got passed down as procedure rather than principle. Do this, then this, then this. And for most of history, that was enough. But here's the observation that the simplified version cannot explain. If you take wood ash and animal fat and mix them together, nothing happens. You get greasy ash. You can let it sit for a week, and you still get greasy ash. The two ingredients do not react with each other. Not at room temperature. Not at any temperature you could reach over a campfire. A soap molecule requires a specific chemical event to form, and that event requires a third party that the simplified version never mentions. The ash and the fat are not the reactants. One of them is a raw material for something else entirely, and that something else is what does the actual work. So what is the third party? It's lye. Specifically, a strong alkaline solution called potassium hydroxide, which you extract from the ash before you ever touch the fat. The ash itself doesn't react with fat. But when you pour rainwater through hardwood ash slowly, over hours, the water dissolves the soluble salts in the ash, and the dominant one is potassium carbonate. That solution, called lye water or ash water, is alkaline enough to strip a layer of skin if you're not careful. Frontier soapmakers tested its strength by floating a raw egg in it. If the egg sat with a patch the size of a thumbnail exposed above the surface, the lye was strong enough. Too weak, and you'd end up with soft, greasy slop. Too strong, and the soap would be harsh enough to eat through fabric. The simplified version gets this wrong by collapsing two separate steps into one. It suggests the ash is a direct ingredient. It isn't. The ash is a lye factory. You run water through it the way you'd run water through a coffee filter, collecting what drips out below. What drips out is the active ingredient. The ash itself gets discarded. If you understand that, you can now predict something new. Denser, harder woods produce better lye because they leave more mineral ash per volume burned. Softwoods like pine burn away with less residue and weaker salts. An oak fire and a pine fire both give you ash, but only one gives you ash worth using. Now you have strong lye water. What happens when it meets the fat? This is where the chemistry the old-timers didn't name, but absolutely relied on, takes over. Fats are molecules built from long chains of carbon and hydrogen, bonded to a glycerol backbone through a type of chemical linkage called an ester bond. When a hydroxide ion from the lye encounters that ester bond, it breaks it. The fatty acid chain detaches from the glycerol. The hydroxide donates itself to the chain, and the result is a soap molecule. One end of it is hydrophobic, meaning it is attracted to oils and grease, and the other end is hydrophilic, meaning it dissolves in water. That double nature is exactly what soap is. It grabs grease from one end and pulls it into water from the other. The reaction that produces this is called saponification, and it was happening in every soap-making pot in every colonial farmyard, named or not. What the simplified version gets wrong here is suggesting the fat is just a filler or a softening agent. It is the other reactant. The fat is not being dissolved by the lye. The lye is chemically disassembling the fat and rebuilding it into something structurally different. This means you can now predict what happens with different fats. Tallow from beef or mutton produces a harder, more stable bar because of the length and saturation of its fatty acid chains. Lard from pork makes a slightly softer, milder bar. Bear fat makes excellent soap because of its high, unsaturated fat content. Each fat produces a chemically distinct soap with measurably different hardness, lather quality, and shelf life. The simplified version has no way of accounting for any of that. Here is the layer that requires the biggest surrender, and it goes against the intuition that older methods are cruder and less precise. The ratio matters more than almost anything else. Saponification is not a reaction that tolerates loose measurement. Too much lye, and the unreacted hydroxide stays in the finished soap, making it caustic enough to damage skin. Too little lye, and you get unsaponified fat sitting in the bar, making it soft, rancid, and prone to going off within weeks. The old soap makers had no chemical balance. They had the egg test, they had the feel of the boiling mixture as it thickened, and they had the inherited knowledge that slightly underlied soap was safer than overlied soap because you could always add more lye water, but you couldn't take it back out. This is the part the simple story makes sound easy because it skips it entirely. The craft was not in mixing two things. The craft was in reading a living reaction with your eyes and hands and knowing when it was done. The mixture was done when it reached what soap makers called trace, the point where a spoonful drizzled across the surface left a faint trail on top before sinking back in, like a thin custard. That moment, and only that moment, meant the saponification was complete and the soap was safe to pour into molds. So here is the new model, compact enough to repeat to someone. Wood ash is a lye factory, not an ingredient. Lye chemically disassembles fat molecules and reassembles them as soap through saponification. The skill was not in having the right materials. It was in controlling the reaction precisely enough to produce a finished product that was safe to use on human skin. Here's a prediction you can now make that you couldn't before. If someone shows you a historical recipe that calls for soft soap instead of a hard bar, you know exactly why it's soft. The lye used was weaker, probably from a single pass through ash rather than multiple passes to concentrate it, producing potassium-dominant soap that stays semi-liquid. Hard bar soap requires sodium hydroxide, which is why industrial soap, once it replaced the homemade kind, used soda ash from evaporated salt water instead of wood ash. Same chemistry, stronger alkali, firmer bar. The ash and the factory are doing the same job. One just does it more precisely. Links to the primary sources and historical soap-making records are in the description.